Hello everyone, welcome back to another physics lesson. I'm Physics Michael, and today we are going to talk about motion graphs. In this video, we will cover three key topics. What are motion graphs, displacement time graph, and velocity time graph? Let's get started. First, let's understand what are motion graphs. Motion graphs can display how objects move in terms of the change in one motion-related quantity against the other. There are many types of motion graphs. For example, the most simple type of motion graph is called displacement time graph or ST graph. This type of graph shows how an object's position or displacement changes over time. The second type of graph is called velocity time graph or VT graph. This type of graph helps us understand an object's velocity changes over time. And the third type of graph is called acceleration time graph or AT graph. This type of graph helps us understand our object's acceleration changes over time. And today we're going to learn more in displacement time graph and velocity time graph. First, let's focus on displacement time graph or ST graph. On the graph, the x-axis represents time in seconds. The y-axis represents displacement in meters. The shape of the graph tells us about the object's motion. From this graph, we can find that the displacement was increasing in the first 3 seconds, which means the object is moving continuously. And we can use delta s over delta t to calculate its velocity. It is just the gradient of the graph. So it's pretty easy to understand that the gradient of the ST graph is the velocity of the object. Here the gradient is equal to 7 minus 2 over 3 minus 0. That's 1.67 meters per second. And after 3 seconds, the displacement of the object does not change. So it means the object now is stationary. So, based on the gradient or slope of ST graph, we can easily tell what kind of velocity the object has in its motion. For instance, if the graph shows constant gradient or slope, it means that the object undergoes motion with constant velocity. And the steeper slope, the greater velocity. Zero slope, zero velocity, or just stay stationary. Or if the slope is negative, it means that the velocity is in opposite direction. And look at this ST graph here. We can see that the slope or gradient is changing, so its velocity is changing as well. Next, let's look at the velocity time graph or VT graph. On the graph, the x-axis represents time in seconds. The y-axis represents velocity in meters per second. The graph tells us lots of information of the moving objects. From this graph, we can find that the velocity was increasing in the first 5 seconds, which means the object is accelerating, and we can use delta v over delta t to calculate the acceleration. It is just the gradient of the graph, so it's pretty easy to understand that the gradient of the weighted graph is the acceleration of the object. Here the gradient is equal to 20 minus zeros over 5 minus zeros. That's 4 meters per second squared. And the horizontal part of the graph here means no change in velocity, so no acceleration. So just like the ST graph, we can use the gradient of weighted graph to find out what kind of motion the object undergoes. For instance, if the graph shows constant gradient or slope, it means the object undergoes motion with constant acceleration. And the steeper slope, the greater acceleration. Zero slope, zero acceleration will just maintain the same velocity. Or if the slope is negative, it means that the acceleration is in opposite direction. And look at this weighted graph. We can see that slope or gradient is changing, so its acceleration is changing as well. In addition, we can find out displacement from our velocity time graph. How? Let's start with a simple situation. Supposing a car is moving with constant velocity on the road. The weighted graph of its motion should be a horizontal straight line like this. The displacement it covered can be calculated by simply using s equals v times t, and that's just a rectangle area under a weighted graph. Here, the area under a weighted graph in the first 15 seconds is 300 meters, so is the displacement. This can also be applied even the object is accelerating or with a changing velocity. For example, the velocity of the another car is increasing with constant gradient, and the area under weighted graph in the first 5 seconds is a triangle. By calculating the area of the triangle, we can easily find out the displacement in 5 seconds is just 25 meters. So, velocity time graph not only tells us about how velocity changes, but also help us find the displacement by the area under a weighted graph. Let's take an example. In this weighted graph, the velocity is decreasing. What is the acceleration and the displacement of the car in the first 30 seconds? Firstly, we can use the gradient of the weighted graph. It is 8 minus 20 divided by 30 minus 0, and the result is negative 0.4 meter per second squared. Here, 0.4 meter per second squared is the magnitude of the acceleration. Negative means the acceleration is in opposite direction of the velocity, so it is decelerating. Secondly, we can use the area under weighted graph in 30 seconds. By calculating this area of the shaded part, we can easily find that the displacement in 30 seconds is 210 meters. Now, let's summarize what we've learned today. First, displacement time graphs show how position changes over time, and the gradient of an st graph is the velocity of the object. Second, velocity time graphs shows how velocity changes over time, and the gradient of weighted graph is the acceleration, and the area under weighted graph is the displacement it traveled. That's all for today's lesson. Thanks for watching, and I hope you now have a clear understanding of motion graphs. I'm Physics Michael, and I will see you in the next video.